Assalamu alaikum wa rahmatullah. Hi everyone. Today I'm going to talk about the role of suprathermality on dust acoustic waves in the presence of polarization and dust charge gradient forces. First of all, dust acoustic waves, commonly referred to as BAWs, are low frequency waves in plasmas containing highly charged massive dust grains. Such plasmas, dusty plasmas, also called complex plasmas, are present in astrophysical environments such as planetary rings and comet tails, but also at laboratory plasmas. The theoretical and experimental studies have shown that dust grains would impact the wave spectra and generate new engine modes like DAWs and dust ion acoustic waves. The main objective today is to investigate how polarization and dust charge gradient forces would impact the propagation of dust acoustic waves under the influence of suprathermal electrons and ions. To tackle this problem, we would use the following theoretical model. We would consider a plasma consisting of suprathermal electrons and ions and negatively charged dust grains. The superthermal character of electrons and ions is modeled using the kappa-deformed Lorentz distribution. The latter would capture the non-Maxwellian behavior in plasmas, and the expression of such a distribution is the following, where we can see the presence of the superthermal index kappa, which is different according to which particle it would refer to. So kappa E refers to electrons and kappa I refers to ions. Of course, the distribution function is a function of the electrostatic potential phi and the velocity of particles. Also, we have the charge neutrality, which means that a plasma is globally neutral in terms of charge. And this is assured by the following condition, where we have the number density of negative charges being equal to the number density of positive charges at equilibrium. Here we have an E0 and D0 and an I0 referring to electron number density, dust ion number density, and ion number density at equilibrium, where ZD0 is the number of electronic charges residing on the surface of the dust grain at equilibrium. The non-linear dynamics are described by the following governing equations. We have the first, the second, and the third equation constituting the fluid model, while the fourth is the charging equation governing the charging of dust grains. In those equations, IE and II refer to electron and ion currents, while the polarization and charge gradient forces are named FP and FCG. Here we have the expressions of currents and forces obtained for our model of plasma. The reductive perturbation technique, RPT, is applied to derive the propagation equation, which is revealed to be a KdV-Berger equation. Here we have three coefficients, A, B, and D, that are influenced by the deviation of electrons and ions from Maxwellian equilibrium, and also the deviation from the equilibrium dust grain charge would have an impact on those coefficients. A is the nonlinear coefficient. B and D are the dispersion and dissipation coefficients, respectively. The propagation equation describes the small amplitude propagation of dust acoustic waves, where both of the polarization and charge gradient forces contribute to nonlinear dispersion and dissipation effects. Using a suitable scheme, the KdV-Berger equation was numerically integrated, assuming a space-dusty plasma. The results are the following. The electrostatic potential perturbation took the form of a solitary wave, where we have the polarization forces or force increasing the amplitude of the solitary wave and reducing its width. On the opposite way, the charge gradient force, FCG, would lowers the amplitude and broadens the wave. As for the combined effect of the two forces, we can see that the results are similar to those of the charge gradient or the application of the charge gradient force, meaning that the latter is dominant over the polarization force for the plasma parameters that we've chosen. Here we can see the impact of electrons' suprathermality on this figure. The suprathermality of electrons and ions are presented by the spectral indexes kappa E and kappa I, significantly affects dust acoustic waves. For kappa E, as it increases, so that the electrons get closer to the Maxwellian equilibrium, we can see that the polarization effect weakens while the charge gradient force strengthens. As for the impact of the ion suprathermality, we can see that the charge gradient effect is more dominant at higher and lower values of kappa I, while it is less pronounced for intermediate values. This is to say that there is a critical kappa I value beyond which the impact of ion suprathermality is reversed. In conclusion, we can say that polarization and charge gradient forces act in opposite directions, with the first enhancing the amplitude of electrostatic solitary waves, and second reducing it. On the other hand, suprathermal electrons and ions have a significant influence on dust acoustic waves, altering the balance between Fp and Fcg. Here we can say that the suprathermal character of the electrons and that of the ions have a different impact on the result of the polarization and charge gradient forces, offering insight into dust acoustic wave behavior and propagation in non-equilibrium plasmas. Here we come to an end, so thank you for your attention.